Now that we're armed with a couple of different ways to algebraically approach a linear system, let's go back and take a look at those strange cases. Now recall when we were graphing, our strange cases were, what if I had two lines that were parallel? So that was no solution. And then another strange case is what if I have a line that lies right on top of the other line, right? And so whatever line we ended up with ended up being the solution. So those were the strange cases that we saw. No solution, we ended up with a ridiculous statement like 0 equals 2. That was a case, that's usually what happens when we end up with a contradiction. All right, and of course when we had this, we had an identity. And we usually ended up, oops, I can't spell identity, right? We usually end up with like 0 equals 0 or something that is always true. So it turns out algebraically we're going to get the same thing. So let's see that. We'll re-practice both skills at the same time and see these strange cases. So the first one, here's my system, and I notice that already I have y already solved for. So substitution is probably the best way to do this because it's already ready for substitution. So all I got to do is come up here and substitute what I know y to be into the other equation. Alright, so there I am, substituting 5/2 x plus 3 into the other one. Solving for x, I'll begin this journey by distributing. So when I distribute here, the 2's divide out, and we're left with negative 5x. Negative 2 and plus 3 would give us a negative 6, and we get 10. 5x, take away 5x, well that's gone, and we're left with negative 6 equals 10. Alright, and this is not true. We can already see that already. It's actually never true. So what does that mean? We have a contradiction here. We have no solution. So if I was to graph both lines here, we'd have one of those cases where my lines are parallel to each other if we did section 8.2 and graphed. So that's what happens. You end up with a totally ridiculous statement. So the algebra continues to lead us to that mathematically ridiculous statement. What about the other one? So solving this system, how about since we've already seen substitution, let's go ahead and use elimination. And how about we eliminate, let's go ahead and eliminate the y. Right? So how do I eliminate y here? Well, crazy, right? Because I need the coefficients in front of the y to be opposites. Right now one's positive 3 and one's a half. So what can I multiply to a half to get negative 3 essentially? So how about we take that second equation and why don't we multiply it by negative 6? Of course, whatever I do to one side, I have to do the exact same thing to the other. So the first equation we didn't touch, right? That's 2x plus 3y equals 9. Second equation, if we distribute, well, negative 6 in the third, right? That gives us negative 2x. Negative 6 times a half would be a negative 3y. And over here, thinking of that over 1, we end up with negative 9, right? Because we end up with negative 18 over 2. And if we go through and try to eliminate everything, the x's are gone, the y's are gone, leaving us with 0 on that side. 9 take away 9 is also 0 on that side. So we end up with something that is always true. So that basically means that this whole line, right, whatever ordered pairs solve this line, essentially solve this system, because our work has showed us that this crazy line with all the fractions is the same as this crazy line without all the fractions. And so that's basically what happens in those strange cases. So nice review of both the substitution technique and the elimination technique, and then the idea of what happens when I end up with something that's never true. We end up with no solution. What happens when I end up with something that's always true? Well, our line, any line you want, is basically the solution to the system. So that should wrap up our algebra. We now know how to solve systems, and we're ready for some word problems.